I think that this section of this chapter is probably one of the more important and more useful ones. It's one of the problems that no matter what you're doing with kinetics, you're going to have to do these rate law calculations. So, I've got a board and some markers. The better markers are on their way soon. But we're going to try. I'm going to have to zoom in and out. But I got me a board. Tie-dye ducks back for day 2. Don't you love this? This is great. At least I'm not sitting in front of the screen waving my hands in your face this time. We're starting with concentration and rate laws. Rate laws are just ways to express the rate of a reaction. They're really straightforward. They show rate as related to concentration of reactants. Because we talked yesterday about the fact, or last class, I don't remember if it was yesterday or like last week, same as always. We're going to talk about how rate depends on reactant concentrations, because remember I said as you run through a reaction, you tend to run out of reactants and the rate will slow down. The rate constant K is a big thing. K is your rate constant, and it determines how your temperature affects rate. At a given temperature, say 273 Kelvin, the rate for a specific reaction will always be the same. It will change for that reaction with temperature and will be different for other reactions. Obviously, if you've ever been in the hallways, not everyone walks the same speed. That's how reactions go too. The magnitude or size of K changes with temperature. I got my binder today. So when you see the generic reaction, we're going to be writing these in terms of reaction orders. Now, what I'm doing here, and you'll notice if you're looking for the generic reaction, first of all, only reactants appear. Products don't affect a reaction rate at all in terms of what we're doing. We're going forward direction reactants only, and you'll notice that the rate in your packet is written as K, A to the M, B to the N. Not A to the A, B to the B. It's not the coefficients that determine your superscripts. They're determined experimentally, and we're going to do that today. They're called reaction orders. The superscripts on your concentration are reactant orders. And it's real literal. If it's a 1, it's first order. If it's a 2, it's second order. You can do reactant orders for individual reactants or overall for a reaction. So your overall reaction order is the sum of the orders of all of your reactants. And we're going to do that here. I've got the very first part set up and you can follow along. It's easy. This is the easy stuff. So my first one, this is the same as in your notes. So if you can't really see it on my board, I am going to zoom in on the board later. But for the top part, I just wrote it so I would have some place to write it down. For this one, K doesn't matter. You look at the concentration and its superscript. First one only has a 2. It's going to be second order. Second order, that's it. There's nothing going on here. And this is the weirdest thing ever, because we're going to call it 0 order. Nothing, no superscript, no order. This one, hate. 1 for H2, because if there's nothing there, it's 1, like always in chem. Br2 is a half. This ain't real. This is one of those things that I'm like, fake. You get a 1.5 order, and I feel no need for that. That's one of those things teachers do just to do. You aren't going to see these. For the last one, 2 on NO plus 1 on O2 is a third order reaction. Those are your overall reaction orders. If we look at this last one, I can say that this reaction is second order in NO and first order in O2. That's going to be important. We're going to keep coming back to that. I put a little chart down there at the bottom of that page talking about how a rate is affected by its concentration. So if I double something that's first order, because it's to the first, the rate doubles. If I double something that's squared, though, the rate will increase by a factor of 4. Always good, legit. For your practice on the next page, we're looking at doubling the rate, the concentration of ClO minus. Your pages may be a bit different from mine. Quadrupling. So if I double something and the rate quadruples, it's to the second power. It's second order in that reactant. We good. Magnitudes and units of rate constants, I don't expect you to know this or do anything with this. Fast is like 10 to the 9th, so what you would call real big. And then anything slower than a whole number, anything lower than a whole number is considered slow. I'm not asking questions on that. This is cool. If K is 0, if the rate constant is 0, you're not going to have the effect from rate from that. Great. Units on rate constants kind of suck. Kind of suck. You've always got to get to molarity per second. Your goal. That's one of the things I hate. Molarity, seconds to the -1. Gotta love that. So my concentration is going to be in molarity, and we're looking again at the change in molarity with time. What you're doing to get these, and I think I added 0 in your packet, 0 order. If I didn't, I will. The units for K, so we're looking to get our units for the rate constant, are going to vary by your overall reaction order. They're going to have to give you a rate that's in molal per second or in molal per minute. So if I'm looking for this, whatever my concentrations are, I need to divide by something that gives me that. So for a first order reaction, all I'll have is A to the first. So that would just give me regular old molarity. If my rate is going to be K times that, K would need to be in 1 over seconds, because molarity times 1 over second gives me molarity over seconds. If my A is squared, then I need to include something else here. In this case, I would still need 1 over seconds, but I would also need 1 over molarity, because I would have molarity squared and need to get rid of it. Basically, for a first order reaction, you start out with 1 over seconds. For every order you go up to that, you add an m in the denominator. So for my second order rate constant, I'd be seconds to the -1, molarity to the -1. If I have a third order reaction, seconds to the -1, molarity to the -2. For a 0 order reaction, I got no units, because it's just K. So it's going to need to be molarity per second or molarity per minute. I think those are in your notes, but I just wanted to go through that again before we get to the fun stuff. Oh boy. Oh yes. Here we go. Using initial rates to determine rate laws, and I'm going to scoot this around. It's going to be awkward, but I want you to see this. Not me. Haha, that's the good stuff now, and you are going to see my arm reaching through. Using initial rates to determine rate laws, let's look at the info we've got here. It's the same as what's in your notes and the same as what I typed up. 4 trials of the experiment, 1, 2, 3, 4. So I did the same experiment 4 times. Oh, this is awesome. This is like perfect. And what you'll see is for each one, the equation, I had some nitrogen monoxide, some nitrogen dioxide, and some oxygen. And I used a different concentration for each time to see what was up. This one should be that. There we go. I used a different concentration of at least one reactant each time, and you'll notice that my rates are in meters per second, but they've changed. They're different for most of the trials. My goal is to figure out why, what I changed that made them different, and how in order to figure out the rate law of the reaction. So I've got 3 reactants that might participate. And this is trial and error. This is going to take you some practice to know what you're looking for. I'm going to start out by comparing runs 1 and 4. Why? Because I've only changed one thing between them. For 1 and 4, I've got 0.10 molarity NO, 0.10 NO2, but I've doubled my oxygen from 0.10 to 0.20. Hold the presses. My rates haven't changed. 2.1 times 10 to the -2nd, 2.1 times 10 to the -2nd. So doubling oxygen didn't do jack crap. Nothing happened. So what I can tell you from that is that O2 is not going to be in my rate equation, because doubling it didn't do anything. So my concentration of O2 doesn't affect progress, doesn't affect rate, and we're just going to pretend it's not there. So now we want to see how doubling NO or NO2, changing those concentrations, affects my rate. Check it out. Let's do then for you're not worth anything right now. So let's look at the difference between 1 and 2. I doubled NO. Cool. I went from 0.1 to 0.2. Look at my rate. It doubled as well. 4.2 is twice 2.1. So I doubled NO, doubled my rate. RA, this is like watching me write upside down on my desk. Rate equals K times. Let's start with NO. Since it is doubled and doubles my rate, it's going to be first order here. Let's move on to NO2. See what's up here. It looks like, we're done with that one. Let's look at a trial where we keep things constant. What do we got here? Let's look at one where we keep, I don't know, something else constant. Where we got here? Make sure I've copied these right. I think this one should be 0.2 also, and that makes more sense. Because check these out then. This is good. We're going to go down to 2 and 3 and go from here. I double here. No, I triple here, sorry. Those are the same. I triple my concentration of NO2. If you do this on a calculator, you'll notice that your rate triples as well. So 4.2 times 3 gives me 12.6. Those are good. So when I triple NO2, I triple my rate, and therefore I get that. It's messily written, but because when I double NO, it doubles my rate. I've got first order for NO2. When I tripled NO2 and kept NO the same, I tripled my rate, and oxygen didn't do anything. There is my rate law for that reaction. This rate law is first order in NO, first order in NO2, and second order overall. The units on my rate constant would be everybody's favorite, m to the -1, s to the -1 for a second order reaction. This is written out in your notes, but it's way easier for me to explain. You've got a practice problem or two on this, I think, and we can go over those if you need me to. If you're having any trouble on the practice problems, please just let me know, drop me an email, and I can either teach a session on them, or you can stop in during office hours, or I can post what you need. Have a great day.